Okay, guys, so we start today with the introduction to the perceptron and the multi-layer perceptron. Very easy material, very introductory, a little bit of history. We thank our people at Harvard for the slides. We really enjoy the slides. So this is in this course there are a few memes. I think you appreciate them. When you go to the slides and you review them, I think it's a good meme. If you know who this guy is, you should know who this guy is. If you don't know which TV series is this, it's okay. It's maybe we're revealing our age. If you know this movie, you should know this movie. The rest is there. Okay, so yeah, the slides are a little bit old, but of course the application of deep learning are all over the news. The slides are from 2020, so there it's ChatGPT 3, right? So that was before OpenAI became the center of the financial discussion all over the world. Let's not go there. These are two interesting stories, right? So they're becoming more and more relevant. So the societal impact of deep learning is also becoming more clear to us. We're discovering that these algorithms that determine our life, actually, they affect the society in a very deep way, right? So, for example, classic example was this risk model that the US court used to find the rates of recidivism, right? So estimate how likely was a person to commit a crime again. So they have to decide bail, they have to set bail. And the algorithm was trained on past court cases. And then people went and figured out that, of course, whether a person was black or white was one of the determinants of whether a person will receive bail or not. Gender bias, right? So, of course, when there is hiring, we all know that, what can we say? How can we say that our hiring practices, they are flawed, as all humans are. So people train models on evaluating candidates, and then they figured out that the candidates preferred male applicants. This is a very long and well understood bias of our society. And basically, when we take actions with a bias, and then we use a deep neural network to learn our actions, then we also teach them to have our biases. So it's very consequential to our daily life. Okay, then this is the historical remarks of deep learning, right? So there are different phases, different eras of deep learning. There are different winters of deep learning, and you can see here, right? So the first people to imagine this electronic brains in the 1940s was actually from psychology. Then there was the XOR problem, right? So the people first did the neural network. They figured out how to do the backpropagation over a network with 1 neurons, and at that point they figured out how the network can be trained, how can you have multiple input and output neurons, how to do backpropagation. And then they got stuck with this XOR problem, meaning that they wanted to show that with a deep neural network you can learn any logical function, and they got stuck in realizing that the network could not learn basically non-linearly separate. They couldn't learn all possible binary function. That's because, as we discussed last time, and that we did SVM, right? Support vector machines. You can imagine that this is a 2 input, 2 output function. Okay, so here you're representing XOR. Here you're representing an OR function. So if the input is 0, if one input is 0 and the other input is 0, then you have this is an AND function. So let's say the blue is 0 and black is 0, white is 1. So in this case, we have 2 inputs, 0, 1, 0, 1. So if we have 2, 0, then the output is 0. If you have 0, 1, then we have 0. If you have 1, 0, we have 0. If we have 1, 1 is 1. Okay, so we can learn this function with one neural network with a linear activation function, because basically we can you teach the network that whatever pair of values is below this line, it will be a 0. Whatever is above this line, it's a 1. Okay, so the network, we can teach a very simple network to reproduce this binary function. And then people figured out that however you train the neuron that you wouldn't be able to learn XOR, right? Because in the XOR you will need two separators. Of course, people got stuck here, but in the 1980s, and then they figured out that you can have multi-layer, and then you can have separability of you can learn non-separable problem, and then the idea of multi-layer perceptron and background propagation came in, and from this one here we also learn SVMs. Okay, so, support vector machines, Wagnis and Cortez in the 2000s. Then there was a big winter until let's say the 2010s, and Hinton, that very famous, he was at Microsoft for a long time, I think. Basically, some of his students, they figured out that the trick was to use this hardware that was originally developed for games for speeding up the computation of backpropagation. And so this guy had Jeffrey Hinton, had his first contribution in the 1980s, and only in the 2010s, actually, he was there to foster the development of the numerical methods that allow us to train very large network. Because basically, we figured out that the power of these deep neural networks is when you have millions and millions of parameters, hundreds of thousands of nodes, and this power was only unlocked when we learned to do the efficient training using the linear algebra that was developed for games, right? So that's why we talk about GPUs, because originally it was a graphical processing unit. It was there to accelerate computer graphics, from the 1990s, when people were playing a lot of 3D video games, and there was a lot of image processing that went along with that. And basically, they figured out that they could use this specialized hardware for gaming, actually for training deep neural networks. And then that is what fostered the development. Then GNNs, adversarial neural networks, were in the 2014. Then the big break in NLP was in the 2020. Bain Jobert Fellow. And the progress is just accelerating from here. Of course, regular inference. I hope you have seen this documentary about the first time the Google engineer, Google DeepMind were able to beat a very famous Go player, and then NLP, right? NLP is what natural language processing is what has been at the forefront of the news in the last 3-4 years. Okay. Papers on machine learning, of course, exploding. Now the trend keeps going up. So this is the landscape in which we approach the topic today. Okay, so the topic is very much at the forefront of the news and daily discussion among people, and we are here to study the engineering basics of this. Okay, so remember that we are discussing this last time. So we said we have a set of input features, and we want to predict a response variable. And in order to do that, we use a data set. The data set has a certain number of entries. Okay, so we have D is the number of features that we have. We are predicting a single scalar variable, and then we have N entries in our data set. And the paradigm that we use here is that of classification. Okay, so in this case we have on the y-axis. So this is a heart disease data set. Okay, so here we have the age, the sex, let's say whether they have chest pain, and we want to predict if they have heart anomaly heart detected. Okay, so if you're going to have an anomaly in their heart function. Okay, so this is the data set that we are using for this presentation today. So this is actually a data set that was collected at the ER, at the emergency room at the hospital, and people came in and fill in the questionnaire. And this is actually a very well-known problem. I'll just tell you a little bit aside. It's a very well-known problem in emergency rooms, right? That people come in with heart attacks, and you have to act very quickly when a person comes in with a heart attack. But a lot of people come in with very similar symptoms, right? Or have chest pain, I have a very high heart rate, I'm overweight, I'm over 60. So people try to develop a model that will able to discriminate the people that were the very high risk of heart attack versus the one they don't, so that they can prioritize them and see the doctor. This is the context of when this was done. Okay, good. So going back to this, we represent the data set, of course, over two dimensions just for simplicity. So on the x-axis, we put the max heart rate. On the y-axis, we put the heart disease. And we are asked to classify whether, based on this heart rate, the person is going to have a heart disease. Okay, so we discussed regression yesterday. This is not a regression, this is classification, meaning that in this problem, you see that for a given heart rate, we have that the person could have a heart disease or not. And this is not conceptually something undesirable, okay? This is conceptually telling you that actually, for a given heart rate, what you observe is that there is a probability of a person having a heart disease. Okay, so the probability of your model, the task of your model, is not that of outputting whether the person classifies as having a heart attack or not, because in the data set you have for that max heart rate, people have both a heart attack and not have a heart attack. But instead, your model should produce a probability. Okay, your model should produce a probability that at that max heart rate, you're going to have a heart attack. Okay, so since we have to produce a probability, we are actually predicting, you can think of it as predicting the log odds, the logarithmic odds, meaning that you want to predict what is the percentage of entries in your data set for which you have a label y equal to 1 for a certain set of feature x versus the label 0. So you're predicting a ratio. Okay, good. So we want to do this. We want to predict probability. In order to do this, we really like this logistic function. Okay, so we like to take a model for the probability, which is as follows. When variable x is low, this is 0. Then when x is large, we go to 1. Oops. So we have this idea that we have a function which is spinned, and minus infinity is 0 and plus infinity is 1. And then we have a certain area of transition where we move between 0 and 1. Okay, so we want to use this type of model. And the way in which we obtain this type of behavior in the function is as follows. We take 1 over 1 plus e to the minus, and then we put a nice affine function, a nice linear function there. We say, oh, this is a nice way for us to convert what is substantially a linear estimator, right? So remember last time that we saw linear regression. This b0 plus b1x is a linear estimator. It's a simple linear function, but we put this in this nonlinear form, in this logistic function. So 1 over 1 plus x, 1 over 1 plus e to the minus x, and over this x we put this, okay? And then it's clear that the function, the parameters that we want to learn are the parameters of this affine function, of this linear function, and these are the b0 and our b1, okay? And here you see a representation of the influence of the parameters. So the slope is controlled by b1, and b0 is the shift from 0. Okay, was there a question? No. Okay, good. Then the way in which we train this function will be to set up this log loss. Okay, so what we want to predict, what we want to take as a loss function is how far away is the prediction of our model from the true ratio of a 0-1 label, and we do so with this log loss function. Okay, so we have that b0 and b1 are the parameters of our model. Remember that the p is produced in this way. Okay, and then the y is the label. Okay, so we go through the elements in the data set y equal to 1 to n. For each of them, we look at we put the x inside the logistic function. It's going to give us a p. Then the y1 is either going to be equal to 0 or 1. So we take 0 or 1 multiplies by the log of the probability, and this is going to be the complement. Huh? So 1 minus So if this is 0, this is going to be 1. This is 1, this is going to become 0. And log of 1 minus p, so the log of the probability. Okay, so this is how we correctly, let's say, account for the accuracy of the prediction of our model. Okay, so when you see this, remember, okay, please, the y's are either 0s or 1, and the log and the p are this probability here. Okay, and then you sum over all the elements in the data set. And then, since you decide that this is the correct loss function to use for this model in which you are predicting the probability of an event, then you will do backpropagation over this, you will do SGD over this, and you will train your model. Okay, so this is a review of logistic regression for the people that didn't do logistic regression either with me last semester or just in general. Good. So now, please review logistic regression. If you have if you want some more material, remember that there is the Harvard course that I follow in my previous classes there. You can also go to the YouTube channel where we discuss it and whatever. Okay, so plenty of material on logistic regression. Now, we want to move from this to the idea of the single neuron, which we call a perceptron. Okay, so if you look at what we did for logistic regression, right? So the X came in, we applied an affine function. So affine for you just means linear, okay? Don't you worry about it too much. So affine just means linear. And then there was this linear function, which we like because again it gives us an idea of a hyperplane, right? So there is a certain region, and we are negative if we are in a certain region. We are positive if we are in another region. So we like this idea of the hyperplane of the affine function. And then we apply an activation function. Okay, so the activation function in this case was the logistic regression. And which was 1/1 plus e to the minus h. Okay, so the h is what comes out of the affine function. And then we applied the loss function. And the loss function here was the logistic regression, the log loss, right? So it was y1 log of p1 minus 1 minus y1 log of 1 minus p1. Okay. And so, you know, if you have multiple input features, you can, of course, stack the models, right? So you can stack this H1 to be a higher dimension. And yeah, and this basically, you could also, instead of take the models in parallel, let's say, have multiple input features, each of them predicting the probability of a heart attack. So you will stack this into multiple estimators, right? And multiple, let's say, multiple rows, each taking a certain input, applying an affine function, apply a certain activation function with some parameters that you wish to learn, and then calculating the loss, and then you sum the loss. Okay. So okay, good. So if we do this into multiple rows, it's not particularly interesting, right? Because computationally it would be very inefficient to run all this computation in parallel. What we can do is that we can try to synthesize everything into matrix form. Whenever you can do something in matrix form, do it in matrix form, because this can accelerate your computation. So what you can do is that you can stack everything and just have an affine function that take a vector x of features in input, produce a certain hyperplane according to these parameters omega. Then you this is going to be this is going to be a scalar, right? So then you have u y hat, and then you put it into the affine function, and then something comes out. Okay. So notice just the trick here, which is something to keep in mind. Okay. So you see here that here we have basically a slope, right? A coefficient for x and a b0. And when we turn this into matrix form, here we have a vector b and we have a matrix omega. We really don't want to carry around this plus b. Okay, this is just a pain to manipulate mathematically and also numerically sometimes. So it's really, you don't want to carry around the plus b. You will not want to just have to deal with an x times omega. So what do? You augment your omega. You augment your x with an extra feature. Okay, and this will be the constant value of x equal to 1. Okay, so when you go to the feature of the data set, you have a first feature which is always equal to 1. Then you have the first entry in the data set for the first feature, all the way to the first entry in the data set for the P feature. Then you go down to the column and you get to the N entry of the data set, where you have the first feature all the way to the N entry of the data set to the P feature. And then for this omega coefficient, you will put the coefficient B as the first entry and all the other omegas down there. Okay, good. Blah blah blah. Remember, this is a scalar, right? So this is a matrix times vector. This comes out. Then we put in the logistic regression, and then everybody is happy. Okay, and we calculate the loss. So here, notice that this is repeated for all of the N in the data set, right? So for each entry in the data set, we have one row, right? So this is a row times column multiplication, and then you speed it up by considering this matrix. And when you do this operation, you do it entry wise, and then you sum for all of the entries in the vector. Okay, good. This should be there. Then we want to do this activation, and this is what we have we call a sigmoid activation. And so now we have synthesized the idea of having this logistic regression into sort of a neat mathematical concept we will call a perceptron. Perceptron from perception, right? So, neuron. I don't want to talk about Greek, right? But the idea is that it's the entity that perceives things, right? Because the idea is that you get an input X, and then the output will be a certain value of 0, 1, which will correspond to a certain response of what you have sensed, right? So imagine that this X is some sort of skin neuron, right? And you want to say if something touch your skin or not, then this will somewhat abstract the idea that you will integrate the response from the different neurons in the skin and blah, blah, blah. Just in a vague perspective, this is the sort of the brain inspiration of deep neural network from which we get the neural adjective, okay? Good. Then, good. Then we move to the next set of presentation. Let me just ask if everything is okay. Any questions so far? Any questions so far? Very light today, okay, guys? Very light. Very light. View full screen. Boom. Question. Okay, so we are here. The idea is that if we want to recover the regression from here, so the linear regression as we saw it last time, basically we will choose this activation function as being the identity function. So it's clear that this mathematical object is at least useful for us, because by modulating the activation function, we can keep this the same mathematical structure, and we change the behavior of the function. So then the idea is that as you change your activation function, you will be able to have different boundaries, okay? Draw different boundaries in your prediction, okay? So let's say that this is the line that corresponds y equal to 1/2, okay? So this is the separator between the positive outputs of the neuron and the negative outputs of the neuron. And then this will be the linear function, right? So if you put the activation to be an identity, you obtain a linear function, you have this boundary. And as you change the activation function, you will have different boundaries. And we can have a nice way of representing nonlinear function. Good. Okay, good. Now, in the logistic regression, we have this idea, again, that the decision region of the logistic regression has to be convex, okay? So without going too much in the details, we go back to the logistic regression example, and we trace the values for which the output is equal to 1/2. So this corresponds to the output in which the logistic regression model has equal confidence for the 0 and the 1 label. And if you draw this label in the parameter space, in the input space, then you will see that this draws a convex set. And this is related to the fact that in the logistic regression, we use an affine kernel. And so we cannot have, let's say, non-convex behavior as the behavior of our model. And this is very undesirable, right? Because we consider this case, right? If the max heart rate is very low, then we are almost sure that you don't have a heart attack. If the heart rate is very high, then we're also very sure that you don't have a heart attack. And so there is only the issue that if your heart rate is in this region, then you have a high percentage of heart rate. So in a sense, we need our probability to go up and down, okay? And this will correspond to a non-convex behavior of the boundary, which we obtain when we set y equal to 1/2. And this is non-desirable, okay? So this again goes back to the XOR problem in a sense, right? So you can imagine that this is the XOR for 0, 0 being 0, and this is the XOR for 1, 1 being 0, and this is the XOR for 0, 1, and 1, 0 being 1, from in a certain intuitive way, okay? So how we're going to do this, because if we just have one neuron, then we only have one, let's say one convex region, we have only one boundary, and we have to decide to go with this model, okay? This model is the one that minimizes our log loss. Not really good. Or we can choose this model, and this model will do the opposite job, right? But we don't have the both models. So actually what we would like to do would be to simply take these two behaviors, right? One that predicts no heart rate at low, no heart attack at low max heart rate, and no heart rate at max heart rate, no heart attack at max heart rate. Say that 10 times fast, and we will want to combine it, right? We will want to combine the output of these two neurons to a linear function, okay? Oh, I didn't start the slide, sorry guys. Because I stopped the share. Good. Oh, sorry, let's go back. Thank you, Simon, for telling me. Here. Pop, pop, pop. Okay, so we're saying the linear one, the nonlinear boundaries, the multilayer perceptron. This is the behavior we were saying, low and high. Sorry, guys, you tell me about sometimes I click the wrong buttons, as you happen in old age. One model that predicts heart attack at a high heart rate. One model that predicts no heart attack at low max heart rate, and then we want to combine the two models. Okay, so we want to have a affine combination of the two models, and the affine combination of the two models, we will want to take, let's say, a linear combination of the two of the output of these two perceptrons. And so, of course, the easiest way for us to do this is to put another neuron that also take the outputs of the two previous neurons, and then again you have an activation function, and then you put it through a sigmoid so that you obtain this nice and beautiful behavior. Okay, and then the idea is that you want to have a log loss function, right? And you want to have a log loss which is calculated on the output. And the question that we cannot answer at the moment is as follows. For us, what we can do is that we can take the derivative of this loss over the dataset entry with respect to the parameters of this neuron, okay? We do not know how to take the derivative with respect to the two entry neurons, meaning when we want to find the optimal values for this set of omegas, omega 1, omega 2, omega 3, we want to apply SGD so that we start with some initialization value, we put it through the dataset, we obtain a loss, and then we want to update the parameters of the network with respect to this. Okay, what is easy for us to see is to say, oh well, if I take Z1 and Z2 as input to my last neuron, what I can do is that I can take the derivative of omega 3 with respect to this, or the derivative of the loss with respect to this omega 3, and I can find the best omega 3 that will maximize my prediction capabilities when Z1 and Z2 are fixed. We do not know how we will then update omega 1 and omega 2 so that the loss is also decreased, so that we can apply SGD with respect to this. Okay. No matter this, but basically the idea is that a single neuro has a simple behavior. The simple behaviors are either increasing or decreasing sigmoids, and then you can combine them to obtain a more complex behavior. Very good. And then it's clear that as you change the parameters of the intermediate neurons, then you have a different behavior. And this can result in a very complex behavior. You see that these probabilities estimates are very nice. And as you make the network deeper, then you obtain more expressive functions. And so it's clear that the type of functions that we can implement with this stacking of these elementary units actually can grow very complicated. Another example is this one here, again going for the representing the separation in between the hyperplanes. So imagine that here is the value in which the neuron output is negative. Here is where it's positive. Each neuron can only have a convex function. So in this case, we have a hyperplane, which is the separating region of the sigmoid function. So this would be, let's say, negative and positive. This will be positive and negative. And when you combine them again, then you can obtain a region which is non-convex. Okay, very good. So the idea is that we have we want to build a set of convex functions, and we want to build this convex function by piling up simple component blocks, and we want to build we want to connect it to some sort of graph. Okay, so we want to have an idea of the connectivity of these elements, providing the complexity of the function that they represent. Okay. Okay, so usually when we talk about DNN, we have an input layer. The input layer is a certain set of a certain cardinality of the inputs. Then we have a set of output layers, and then we have an output layer. Okay, so the input, that's where we take the features in the data set. The output is when we spit out the predicted label. And then at this output layer, we will compute the loss between the true output and the output that was predicted by the network. So how do we obtain the output as a function of the inputs? So the idea is that the inputs that get multiplied by the entries of the weight matrix. Okay, so you can imagine that we have two inputs. Okay, we represent the inputs to these two neurons as a linear combination of the network inputs times the matrix omega. So these are the entries of the matrix omega, omega 1, 1, omega 1, 2, omega 2, 1, omega 2, 2. This will produce the N1 and N2. Then this N1 and this N2, they go into our activation function. You see here in the activation function, we have again the weight matrix plus a certain bias B. Okay, so B is called the bias. And then the output of the neurons will be the sigmoid. So sigmoid, remember, is the 1 over 1 plus e to the minus x. And so you have the sigmoid coming out of the first perceptron, the sigmoid coming out of the second perceptron. And then they both go into the output layer, and this is where we compute the loss function. Okay, good. So a single neuron can be a logistic regression or linear unit. So the choice of activation function will determine the type of function that we have. And then we combine, we stack, we connect these units in order to obtain a more complex behavior. And then what we obtain is a very high expressive power in which we can produce very complicated nonlinear behavior in the network. Okay, good. Okay, so next presentation. See if I remember to turn on everything. Next. Any questions so far? Any questions? We take a break soon, guys. So let me go into full screen. And then let's not forget to share. Good. Okay, now we can discuss the activation function, the loss function, outputs unit, and some architectures. Because so we saw so far that the choice of activation function will determine the type of nonlinear function we can represent with the neurons. And people figured out that you can have different behavior by imposing different connectivities in the network. Okay, so here it's a nice incomplete set of architecture for neural networks. So this is just for let's say for a simple simple vocabulary for us to describe neural networks. Okay, so the perceptron is a set of input neurons and just output neuron. Okay, so the input cell just takes the values in the data set, and then you apply the nonlinear activation, you get an output. Very good. Then you can make them deeper, and you will call this a feed-forward network. And then if the network becomes fat in the middle, then you will call it a deep feed-forward network. Then in this class, we're going to see the RNNs, which is recurrent neural networks. So these are sequential models in which you can input sequential data, and let's say the network keeps receiving inputs at each time it's used, and these intermediate nodes, they have a memory of the previous values that have been input in the network. So this type of networks, they are not used one shot, but they are used sequentially. So you have a set of inputs, and for each set of inputs, the network produces a set of outputs. Then this RNNs that have been improved into an LSTM module. We're going to see later. Basically, the idea is that you have a control variable that decides whether the memory should be kept or should be refreshed. And this has been still improved in the literature through these gated recurrent units, in which you have a particularly efficient way of learning this gated connection that decides whether the memory should be kept or refreshed. Okay. Then another architecture that we really like are autoencoders. Autoencoders are as follows. You have a set of inputs, and the inputs are equal to the outputs. Okay. But what the network does is that it has a choke in the middle of the network. So the idea is that you take the inputs, you reduce the dimension of the inputs down to a small fraction of the original dimension, and then you re-explode it out, and then you ask the network to produce values for which to find the configuration for which the input of the network is equal to the output of the network. You will ask yourself, what is this nonsense? Why would I want to do this? And that's because you want to get to this representation in the middle, which is very compact, so it's very dense. And so it can be used for as a low-dimensional representation of your high-dimensional data. Okay, so imagine that you have an image. Okay, an image is a very large size, and and it has different colors, and it has different channels and so on. But actually, the information contained by the image is much lower, meaning that the pixels are very much correlated. There is a very high correlation in the pixel, and so for you storing the information of the image using the representation that we have in terms of, let's say, RGB, it's very inefficient, because there is a lot of redundancy. So sometimes it's very useful to take a representation in higher dimension, which is very sparse, okay, and condense it down to a representation which is very dense. And this is the role of the autoencoders, okay? Variation autoencoders, they count on some probabilistic kernel to represent the features, doesn't matter now. And then Markov chains, I guess maybe some of you have seen Markov chains, and then they can be generalized to some deep architecture in this Hopfield network, Boltzmann machines, the restricted Boltzmann machines, and deep belief network. Okay, so these are older architecture that are not used so much currently, but it's all useful. And then when people talk about deep neural networks, they use a certain let's say, a certain nomenclature. So usually networks are organized in layers. Okay, So in this case, we have an input layer, and then we have a set of hidden layers, which is five hidden layers, and then we have an output layer. And generally, if I had to design a network for a learning problem, my general way of going about the design of the network will be as follows. I would want to have an expansion phase of the network. So I will want the network to start by moving high dimension, right? So in this case, we go from 6 neurons to 500 neurons. So we really blow up the space in which the information is represented. And then we will have a contracted phase of the network in which I shrunk down the representations, okay? And this again goes back to this discussion that we had last time, which is as follows. If you have a problem and you want to use, if you have a complex problem, you could either find a complex algorithm to solve it, or you could try to bring your problem to a high-dimensional space in which the problem becomes easy. Then you use an easy algorithm on a higher dimension, and then you obtain your answer. Okay, so let's say that you conceptually, right, you have two choices. Either you have a complex algorithm on a low-dimensional space, or you have an easy algorithm on a high-dimensional space. The two problems are conceptually, okay? Conceptually, the two problems are equivalent. And the answer of deep neural networks is that they like to have a simple algorithm in a higher dimensional space. Usually, they train well over this regime, and this is why you usually have this architecture. Good. Okay, so usually we talk about neurons and input and output of the neurons. This is an affine transformation. Then there is an activation function. And as we said, we go from the input layer, we pass to the hidden layers, we get to the output layers. And then once we have the output, we have to apply a loss function, okay? So in linear regression, we will take an L2 loss. In logistic regression, we will take a log loss. The idea is that we have a function L, right, this calligraphic L, that tells us how good is the output of the network as respect to the label that we have in the dataset, okay? So we have to ask ourselves, how do we measure the goodness of the output of the network with respect to what we were expecting, what we have in the dataset, and of course, different type of problem score for different loss function, and the choice of loss function is another crucial aspect of the training of deep neural networks. Easy, hidden layers. Yeah, different architecture one can have. You can choose to have a fat and shallow network, to have a long and skinny network, because of course the number of nodes will determine the complexity. So usually your complexity is restricted to have m nodes, and you can decide how to organize the m nodes in the network so that you have the best possible performance. Because the number of inputs is specified by the data, the number of outputs, in this case, it's usually scalar. In our discussion, will be usually scalar, but again, is determined by the data set. And usually the complexity of the machine that you have will determine how many nodes you can have in the network. And so as an algorithm designer, you are asked to figure out how to organize these nodes into a set of layers, right? So what is the relative size of the layer and the number of layers? Again, input layer, hidden layer 1, hidden layer 2, and output layer. Now we can discuss the choice of loss of activation functions, okay? So as we said, the activation function introduces a nonlinear behavior in the network. And what we want from an activation function is that when we take the derivative of the output with respect to the parameters in the network, we will have a derivative of the activation function, okay? So we're gonna see this later when we do this in principle, but I think you can understand it intuitively, right? So when we train the deep neural network, okay, let's go back here. When we train the deep neural network, in a sense, we will have a forward pass when given the input, we produce an output, and you see how good the output is with respect to the label in the dataset. And then we'll have a backward pass. Okay, in the backward pass, we see what is the value of the loss, and we want to adjust the weights of the network so that the network will produce a fair output next time around. Okay, so we want to apply SGD as we see it last time. We have the current weights of the network. We apply SGD. We want to obtain new weights of the network using the gradient. The gradient has to be the gradient of the loss with respect to the weights of the network. And it's clear that we have to figure out how this is done because we have multiple layers. But basically, you understand that in the backward pass, we will have to propagate a signal from the output to the input in which we tell each neuron how to update its affine function so that we take one step in the decreasing direction of the gradient. So now that we understand why the gradient plays a role, you will see that this activation function should be such that when I take the gradient of this activation function with respect to its input, then this gradient should not vanish. Okay, you see that let's say you will want, for example, the output of a neuron to be very sharp, right? To be either 0 or 1. And it's clear that this is what you will desire if you want the output of the neuron to represent, for example, a class, right? Or whether a certain feature is present or not in the neuron. But the sharper is the transition between the 0 and 1, the output of the network. The sharper will be the derivative. And so we have very large values of the derivative. And when your neuron is giving you either values of 0 or 1, then your gradient will be very small. Okay, so this function f, right, has a desired behavior, which is to go from 0 to 1 and to have a certain transition, a definite transition between 0 and 1. But you want that the gradient never blows up and is too large, and never vanishes, never become very, very slow, very, very small. So in the choice of function that you have, you're trading off what is a very sharp behavior of the network, which is desirable in many situations in which the output of the neuron should really be a signal of the type 0, 1, right? Keep or leave class 0 or class 1. And the fact that it has to be smooth enough so that the gradient is never too large or never too small. Okay, so when you train the network, you will see that the issue that you have is usually that either the gradient vanishes or the gradient blows up. Okay, because these issues of the gradient vanishing or blowing up, they are repeated, they present themselves at every layer, so the problem is compounded from layer to layer. You're going to experience this by yourself. The point is that we have to choose functions, and in the choice of functions, we want, again, nonlinearity, a nice gradient behavior, but also a certain ease of computation. Okay, so it's clear that not all the functions have the same ease of being computed in a computer, right? So operations like exponentiation are somewhat easy in a computer. For example, taking sines, taking logarithms, it's a harder operation for computers because they have to rely on some interpolation, and the way in which the error propagates when you compute this derivative is very tricky. So there are also some numerical consideration on the type of function that we can use, and so that's why we have agreed that a nice set of activation functions that we want to use are the sigmoid and tan H, ReLU, leaky ReLU, generalized ReLU, we're going to see later, soft plus and swish, and they are represented here. Again, this idea that there's an inherent complexity of obtaining this derivative, and that the representation of the function can be affected by the precision with which you can calculate either the function if its derivative, something that we discussed in the other course that I have. So just to let you know that you can still join the other class on the numerical recipes for machine learning. Just the idea. So as we said, the sigmoid function is 1 over 1 plus e to the minus x. This is the function and this is the derivative. So sufficiently smooth. Sometimes too smooth, right? So then we have tan H. Tan H, we repeat as this formula that you remember. So again, e to the x is something that we can numerically do somewhat efficiently in a computer, and also the derivative is somewhat nice. Now, now here comes ReLU. Okay, ReLU is very simple to do an inference because we just take the max between 0 and x. ReLU stands for rectifier linear unit. So a rectifier comes again from the circuit discussion, right? The idea is that this is a linear function, and it's rectified, meaning that instead of going to 0, it goes to 0. Instead of going negative, we clamp it to 0. So it's as if you put a diode, and when the voltage goes down, then the output of the diode remains 0. Okay, so this is where the rectified vocabulary comes from. So the issue with the ReLU is that it's the function itself to compute is very easy because it's just max of 0 and x. So you can imagine computationally this is very easy. It's a very easy nonlinearity to deal with. But of course, the issue is that the activation, the derivative as a point where the derivative goes to infinity. Okay, so you see that here, if you approach the function from the left, the derivative is 0. If you approach the function from the right, the derivative is x. So actually around 0, you don't have a definition of the derivative. So it has discontinuity in the derivative. And basically you have to ask yourself, can you take a derivative with respect to a function that has this type of discontinuity? The answer is somewhat mathematical, but basically the answer is yes, because you can take any supporting hyperplane to this point. So basically any plane that doesn't intersect the function, doesn't matter, just math. But basically, people have decided the nice way to do this is to call the derivative 0, right, on the left, and x to the right, and 1 to the right. So you see that the way you transition between 0 and 1 creates some numerical instability. Of course, in the modern solver, this has been addressed very effectively, so you will not see Python giving you an error if you use a ReLU activation function, but conceptually you guys understand that there is a big jump in the derivative between 0 and 1 when you do training, and this creates instability if during the SGE steps, right, you keep bumping between +1 and -1, +1 and -1 in the derivative, right? So this creates some instability in the training process. So in order to do this, people have added some smoothing around the corner of the ReLU, and they have created this exponential ReLU or this ELU. I'm not going to bother you with this, but basically the derivative is a little bit nicer because the transition between 0 and 1 is on the slope that you can control. Then other ways of smoothing out the ReLU are with this soft plus, so log of 1 plus e to the x. This is you can think of this as a soft way of applying the max between 0 and x. Okay, so this function is called the log sum exp. So if you have, let's say, the max of x1 plus x2 plus x3, you would approximate you could approximate the maximum as the log of e to the x1 plus e to the x2 plus e to the x3, and you can verify by yourself that this is a sufficiently good approximation of the max of the x1, x2, x3. It's a continuous approximation. And so if you apply that the log sum x approximation to the max between 0 and x, then you will get log of e to the 0, which is 1, plus log of e to the x, which is e to the x, and then you will take the log of this. And then we can also take x sigmoid of x because the derivative becomes a little bit nicer, and people are always experimenting with different activation function. As far as you are concerned, try to always use either ReLU, Liqui ReLU, or ELU, and then you will build an understanding of how to choose good activation functions for the problem that is at hand, and there is really sort of a feeling that people have with respect to which function to take. So I think we take a quick break, guys. What do you think? We're on the for an hour, so let's take a quick break. Maybe 5 minutes, guys. Okay, take a 5 minutes break. I'll see you back at 35. See you back at 35. If you have any question, you let me know here. Otherwise, yeah. Otherwise, I'll see you back in 5 minutes. Okay. Walk around, drink some water, stay healthy, and I'll see you back here. Okay. Yeah. Any questions? You can let me know. Okay. A couple of minutes. I'll start.
Hello, sir.
Yes.
I
Go ahead.
wanted to in other class. I'm curious if that TA is also in the group.
Yeah. It is. Yeah. Nafal, can you help Barry register for the other class? Because I think, do you need Barry? You submitted the form, right?
Sorry, I didn't hear right.
You submitted the form, right?
The form?
Yeah, there is a form for manually adding the course, right?
Oh, I think I didn't have that.
Let me find it.
It's just I free up the time at Tuesday, but the one at Friday that's stuck with my
No, Friday
gym.
there is no class on Friday. Yeah, there is no class on Friday.
Yeah.
Can you imagine hearing me talk for 3 hours a week? I cannot even convince my wife or my baby to listen for me that long. And there is the form registration. Here's the form. Okay. Okay, good. This is the form. Share. Yeah, Nafar, can you share the request edit access? Is Nafar here or not?
I will send you.
Ah, okay, yes. Maybe post it here, Nafar, because I think many people want to take my other class, I've been trying to convince everybody. Guys, please just come, just take my other class. No, because, okay, I can accept that students don't find me very interesting and they don't find the class very compelling. That's fine. But what we're trying to do is to have this group approach, right? So this people working always in group. And in the other class, we have 11, 12 people. 12 people now with Barry joining. We have 12 people, which means that there is less opportunities for students to meet new students, right? So for me, really, the topic of the class is secondary, meaning that you guys will do a lot of self-study, right? So you will understand, you will explore the material by yourself, in a sense. But really having the students work together, it's really nice. And when there is a class, right, and I just sit down for like 2 hours and the students are just presenting the material, that's when I feel happy. That's when I feel that you guys are learning something, despite how bad I am as a professor. So please consider joining the other class. Okay. Okay, good. So let's go back to this presentation material again. Hopefully, in the next lessons, in the next classes, I can manage to do much fewer frontal teaching. Once you guys will start presenting your own project, it will be much more interesting for everybody, I think. Yeah, good. Because Barry came from my lab on machine learning. Barry, do you want to share some words on how much you enjoyed the class?
What?
Do you want to share some words on how much you enjoy my Python for machine learning class last semester? It was great, right?
At the ending, I was a bit confused because it was like almost the end of January and all the other class already ended and the score is submitted, and we're still having the final project.
Okay. Let me explain. Because for the final project, we usually give the students as much as possible, right? So we give them like a month because basically, because all the classes, right, they all try to give extra courses, extra classes, extra stuff at the end. So we just wanted the students to have as much time as possible. So we put the presentation 2 days before we have to submit the final grades. And so, but I mean, the students can finish the challenge whenever they want, right? It's just that we try to make the presentation as late as possible. But of course, it's only the final presentation, right? You can prepare everything and do it ahead of time. And Barry, that's what you did, right? You prepared the slide and the presentation ahead of time, right? You didn't rush.
Yeah. We did took our time to finish the final.
So that's what Barry is referring to. Okay, I'm not there torturing you. Like the last month of class, you can do whatever.
No.
More?
What?
I said the last month of class there is no lecture, right? We just wait for the final presentation, basically, right? There is no lecture.
Yeah, basically it is.
Okay, I wanted a more strong endorsement of my previous class, but it's okay. I understand.
You want something that will be very encouraging.
Exactly. I was counting on you for
Okay,
convincing.
I mentioned this class with my father, and my father said, "Hey, you should take more class from this professor." Is that
You should
encouraging enough?
you should tell your father that he's also welcome to take my class. We can just put him in, and he can just participate to the challenges. I'm sure he has a lot of wisdom to share with the students.
Okay.
I guess I guess your father has better stuff to do, but anyway, maybe he wants to learn about deep learning. Okay, guys, forgive my amusement here. Okay, let's go ahead a little bit. Again, I don't want to talk too much, but I'll try my best. So now we discussed the higher level connectivity. We discussed the influence of the activation function. Then let's discuss the loss function next. So So the new loss function that we discussed today with respect to last time is this log loss. And the idea is that we want to predict the likelihood that a person has a heart attack given the inputs, and it's a function of the weights. So this is this probability of yi omega given xi. And the way in which we get to this formula is as follows. We assume that the probability that a person has a heart attack is independent from the probability of another person to have a heart attack. So we assume that all entities in the dataset are independent, which is reasonable, since during the collection we don't expect any particular correlation between the entries. And so what we want to do is that we want to maximize the log probability that our prediction is correct. And this is how we come up with the log loss. And then we have to sort of imagine what other losses we will need. And a way for imagining losses is to go back to the model that we discussed last time and saying that in general, we expect that the output is a function of the inputs plus some independent noise. Okay, it's clear that what the network can do is that they can try to match the function in the expression, but they cannot match the noise. Okay, so the noise is independent from everything. So when the neural network is learning from the data set how to predict the output, it can predict the deterministic part of the output, but it cannot predict the noise. So if you know what is the noise model that you assume on a certain set of data, then you can reverse engineer this loss function that we're discussing now, so that you minimize the closeness between the true values in the prediction by accounting for the distribution of the noise. What am I saying here? I'll try to elaborate it as compactly as I can. So imagine now that we are doing logistic regression, and the output of the model is y is equal to omega x plus some Gaussian noise. Okay, so then we know that the true model, right, it's omega times x. So what we expect the deep neural network to learn is also this function omega times x. It's going to learn it from the data set. But the noise is going to be there corrupting the measurement, which means that the distribution of the noise is going to be y minus y hat squared divided by sigma squared and multiplied by 1 over 2 pi squared sigma, meaning that if I take all the prediction of the network and I put them in a histogram, right, I'm going to say that the prediction error as a Gaussian distribution. And the Gaussian distribution has a certain variance sigma, which is the variance of the noise which is added to the data, and the mean is 0 because the prediction has the same mean as the true value. Okay, so in a sense, by assuming that the noise in the model is Gaussian, we obtain that the best way of measuring the closeness is according to the Gaussian distribution, the underlying Gaussian distribution, which values, let's say, which penalizes the error on a square term. Okay, so in a sense, there is a natural pair. There is a natural pairing between what is the noise that we assume on the measurement of the data and how we choose the loss function. Okay, so try to follow me. The class really doesn't go into this direction, but I'll try to give you an intuition. Now, let's go to the heart attack case. Okay, how do we imagine that a person is going to get a heart attack? Okay, we're going to assume that given given the body features, right, given the heart attack, the BMI and the height and the age and blah blah blah, he has a certain probability of having a heart attack or not, and this probability follows a Bernoulli distribution, meaning that this is the probability of getting the PI is the probability of having a heart attack given your body features, given the measurements that we did, and then you toss a coin, right? And the value of the coin will determine whether you have a heart attack or not. Okay, so the PI is sort of the baseline the parameter of the Bernoulli distribution. The YI is the random outcome. Okay, which is a reasonable assumption to do because because we have no reason to because we have no other reason to assume that there is a different mechanism that generates our observation, right? So the simplest way in which we can measure the observation is as if your body condition determines the probability that a coin gives you head or tail, and then every time you enter to the ER, you toss the coin, and you land on the head or the tail, depending on the probability of the coin, which is determined by the features, okay? Then, if you choose that this is the way in which your data is generated, your labels are generated, then the loss will simply be related to the logarithm of this, of the probability of observing 0 or 1 according to this, this Bernoulli probability, this time cost probability, okay? So this is to say that sometimes, right, the way in which we choose the loss function really has to be matched conceptually, philosophically, let's say, to the way in which we imagine the data is generated, okay? Then, of course, you have multiple categories. Then you will have a multi-Bernoulli distribution, so a Bernoulli distribution with multiple outcome, and this is what we call the binary, the cross entropy. Okay, so when you talk about cross entropy, there is always the binary cross entropy, which is the case for two outputs, and then there is the cross entropy when you have more than one output. So again, we come to this sort of design choices. Okay, so let's say that your output is binary, right? So your network has two output, either 0 or 1. So the output distribution looks Bernoulli, okay? Then the output layer, we're going to choose it later. And the loss function is it will be the binary cross entropy. This is what we just discussed. Then let's say that your output is so for binary classification, sorry, got lost a second. So here we still have to decide which output layer we're going to pick, okay? Because we have to decide how to pick the output layer, right? So the output layer is going to be the probability that y1 is equal to 1, and so the output probability is going to be a sigmoid, and so we're going to calculate the loss function over that. Very good. So now we know that in our little table we have output is binary, output distribution is Bernoulli, output layer is a sigmoid, and the cost function is a binary cross entropy. Now, let's say that we have multiple outputs. Let's say that we have multiple categories. Let's say we have 10 categories. Okay. Let's say they are classifying the digits as written on a piece of paper. So we have 10 different categories because we have to decide which digit was written. Then the output distribution will be a multinomial. The loss function we said is going to be the cross entropy. And what do we take as the activation function? Let's go out. So here we have an input, out, and the output is going to produce the probability that the label is equal to 1, is equal to 2, or equal to 3. Okay? Very nice. So the input, let's say it's an image of a digit, and the output is whether the digit was a 1, or a 2, or a 3. So this is very nice, makes sense, because again, we would like our output to be meaningful. So we would like our output to be a true probability distribution. So the question is, what do we take as the output? Well, we know that these outputs, they have to sum up to 1. Okay, so what we want to do is that we want to add a normalization here to our distribution. Normalization to the output of the network so that this becomes a probability distribution, so that in the sense that these three values, they sum to 1, okay? So the network here is doing whatever it does. Then it comes here, and there is going to be an activation function. The activation function is going to produce a score, 3 scores, A, B, and C. And then we want to have an extra layer that has no parameters, okay? So it's not trained, right? But it simply normalizes the probability to, so it normalizes the probability that, let me say it again. So we have this score A, B, and C. So we want to have a layer which is non-trainable. And the role of this layer is simply to normalize the sum of the output to be equal to 1. Okay, so that we have probability for A, B, and C. And when we sum it together, we obtain a 1. Okay, so this is just a normalization. So it has no parameters, it cannot be trained, and it is e to the phi x divided by the sum of the scores. Okay, so we normalize we simply normalize by the sum of the scores so that the sum of the output is equal to 1. And we call this object a softmax, okay? So this is the output of the sigmoid, and then you pipe it down together. If you do a couple of calculations, you see that you can simplify everything like this, okay? So we call this a softmax unit. Very good. Okay, so now we have this discrete multinomial softmax cross entropy. Very nice. Now let's say that we have a continuous type. The output distribution is Gaussian. The function is the MSE. What should we take as a layer? Let's go here. Remember, so here we get a final layer. So what we want to do is that we want the y hat to be an omega transpose phi of the previous layers. And so this is just a linear activation function. Okay, we're not doing anything. I'm just giving a linear activation function. And then if a continuous type, we have an arbitrary distribution. The cost function is generative adversarial. Then you will have to choose some other functions. But basically, the table continues. Okay. So, for example, what we haven't discussed here, for example, what happens for NLP, right? So, natural language processing. How do you calculate the goodness in the natural language processing, and so on and so forth. Okay, but the story continues. And people are always considering new problems with new activation functions that require new loss functions. Good. Any question? Otherwise, we do the last set of presentations before we all go crazy. Listen to my ramblings. Screen. Okay, last presentation, guy. And then I'll let you guys go. And I'll be waiting for your feedback on the final challenge. Now we have discussed almost everything. So remember this set of slides that we said last time. So let's go through this again. Yeah, it was in the last presentation slides. I don't remember if I presented it. No matter. So let's say that we do the following. Okay, we can spend some time on this. Somebody gives us a function to approximate with a deep neural network. This is something very reasonable. Okay, maybe let's say this x sin x function. It's very hard to store in the computer because in order to store the trigonometric function, we need some memory table. And people say, "Oh, I don't want to do that. I just want you to give you the function as it is, and you give me a neural network that embeds this function." Very, very reasonable request. Okay. Similarly, imagine that there is some specific function that describes some behavior of objects. Let's say there is how much load a certain wall can take under some condition. You know, in the case you will have, let's say, a lot of measurements, right? And you will just want to translate these measurements into a prediction, and you know that if somebody asks you for a certain property, you will just go and look at the entries in the data set that corresponded to the measurement, and you will take, let's say, the closest one of the average of the two, as you would do in, let's say, in the K and N. So it's clear that what we want to do is that we want to take a function which is represented through discrete points and have a smooth approximation. Okay, so the keyword here is a smooth approximation. So instead of doing the prediction using the data set that you have collected, you want to build a neural network that smoothly approximates to the values of the function, even if the function is simply y equal to f of x. Okay? In this case, again, think that we have one input, one output, and a simple function, which is given to us as a set of measurements, and we just want to have a neural network that produces a function that crosses these points and otherwise doesn't jump too much up and down. Okay? So this is a very reasonable, let's say, engineering use of deep neural network. Okay. Good. So the experiment is the following. We have this x sin x function. Let's assume that it's very difficult to compute. So in order to evaluate this function in a computer, a guy created a table with 1 million points of this function. And whenever a user asks for a certain value of the function, the computer goes in the table and it gives you the corresponding entry up to the third digit of the request of the users. Then somebody comes to you and tells you, "Oh, this is unacceptable. This takes too much memory." if we had to store this in deep neural network, it means that we wouldn't need to maintain a search capability over this data set. We can throw away the data set and just give the deep neural network. Very good. And then they tell you how big do you want your neural network to be, and this is what we're seeing now. Okay, good. So here we have a real activation function. This is the function that we're trying to approximate. We train this simple architecture with just one hidden node on the data set that you have. And we, of course, obtain this as the best approximation possible. Why? Because the neuron learns that it can get a good fitting over this point. This is balances out to 0. So when you run the SGD, this is where you land. Of course, this is not acceptable for us. So what do? We add one hidden neuron. Okay? If we add one hidden neuron, we know that now we can do this sort of fine combination of the output of these two neurons. And so now we have one slope from this guy and one slope for this other guy. So we know that if we concat, if we place them in parallel, then we can have two slopes, and then the rest is 0. Very good. Again, we run SGD. And SGD teaches us that this is the best approximation that we have. Very large error here, so we're not too happy. So we add another neuron, and so on and so forth. Okay, so we have seen that by adding neuron, we can approximate this function. Beautiful results, right? That came up in the 1990s. Okay. Which says, give me any continuous function f defined on a bounded domain. Then we can find a neural network that approximates f with an arbitrary precision of accuracy. So this theorem, it's called the universal approximation theorem, and it says that whatever model you give me, whatever function you give me, I can produce a deep neural network that can approximate this to any degree of precision that you want. What is the price that you pay? The price that you pay is in the number of neurons. It scales very poorly with the accuracy that you want. And also, this theorem it works for only one hidden layer. Okay, so this theorem says I have a hidden layer. I let the hidden layer go to infinity. When I have the hidden layer go to infinity, then I can approximate any function. So this theorem is not really, let's say, a constructive theorem. Like, it doesn't give you the most compact neural network. It doesn't give you the best architecture of the deep neural network. It just tells you that mathematically, in the class of all possible neural networks that you can build, there is one architecture that can approximate the function with infinite precision. Okay, and of course, before we were just stacking neurons horizontally, but people know that if you stack them vertically, then you get more expressiveness. And if you combine the vertical stacking with the horizontal stacking, then you get the best approximation possible. Okay. So remember this. There are some theoretical guarantees to the performance of deep neural networks, but these guarantees, they are not, let's say, they're not as useful as some other results that we have in engineering. For example, think about the Nyquist theorem, right? The Nyquist theorem tells you that you should sample a function at twice its bandwidth. And really, this is what you need to do, right? So the theorems gives you a very precise number at which you have to sample a function for perfect reconstruction. And if you sample below the Nyquist rate, then you know the type of error that you're going to incur. For deep neural networks, since they are more general architecture and they are maybe mathematically harder to study, then we don't have such a strong result. We just say, oh well, if we have one layer, infinite number of neurons in the neural network, then we can approximate any function. Not particularly compelling, but again, useful mathematically. Good. We go back to this this image that says take a data set which is not linearly separable. Then it's clear that the trick to do here is to change the representation of this set from the Cartesian coordinate to the polar coordinates. Okay, because if we represent this setting in the Cartesian coordinate, then it's very hard for us to imagine a simple boundary for dividing the yellow and the blue. But if we move these to polar coordinate, then boom, we have a simple linear boundary to separate the two sets. And this is sort of what a neural network does in our understanding, right? So simple processing, they help us obtain a useful representation, and then we can perform some simple operation at the output of the network to obtain the desired output. Okay, so again, there's the idea that most of the network learns a useful representation, and then the output just does a simple regression, a simple linear combination. Okay, so we can also visualize this. So if you give this set into the input of the network, and we let the network learn, then let me see, what is this slide? Yep. Then the network will learn to represent the data in a way where separation is simpler, although it doesn't look that way. Okay, and if you do with convolutional neural networks, it's sort of easy. So remember this data set here. So this data set here is the first data set that has been used by pioneers of deep neural networks. So this is the handwritten data sets of digits. So this was used in the post, right? When you used to write mail back in the 1200s, okay? When you used to write numbers with an actual pen over actual papers, then you will put it in the mailbox. And one of the first application of, let's say, vision algorithms was to try to classify the digits of the zip code, right? So that when you write the zip code, the mail will be automatically parsed. And yeah, so the data set contains all the different digits, and they're being recorded. And what you can do is that you can try to use a deep neural network to classify the digits. So this is a multinomial distribution. So the input is an image, 220 bits, and the output are 10 possible labels from 0 to 9. And then what we can do is that we can sort of go to the intermediate layers and see what the intermediate layers learn about the number. So you see that, let's say, a first layer is outlining the edges, right? So you see that here there are different ways of representing the edges of the object. Then here there is some filtering. Here there is some edge detection. Blah blah blah. And then you see that as you go deeper into the network, you start from a natural representation of the image to a more abstract representation, where then, let's say, you are counting the number of corners in the number, you're counting the number of horizontal versus vertical line, and then based on these features, then your last output will take a decision as an SVM would, basically. Okay, so this is something that we know. Okay, good. So now this here is also a very cute image. So here is the following. So we are on the MNIST data set, and we have here the number of layers in the network, so from 3 to 11. And here we have the accuracy in detecting which digit it is. Okay, so you see that if you start with the total number of neurons is the same, and then you change the number of layers. Okay, so it's a fair comparison in the sense that the number of neurons is the same, and you change the number of layers. So here you see that you have a shallower networks versus a deeper network, and you see that deeper networks, they do better than shallower networks. Okay, so this seems to say that we should have more layers instead of fewer layers, but then there is the other side of the coin that says that actually there is a more complex story, and the architecture of the network really has an influence on the type of performance that you can observe. So here on the x-axis, we have the number of parameters. Okay, so the total number of parameters, and here again we have the accuracy. So what we saw right now, we're fully connected network. Okay, so this was the 3 versus the 11 net, right? So here it says that the 3-layer network performs worse on the test set, even with similar number of total parameters. So this is the same story that we have here, right? So 3 layers does worse than 11 layers. But there are some other architecture that we're going to see in a couple of weeks, maybe, which are these convolutional networks. These convolutional networks is a special neural networks that we're going to see after the first challenge. And basically, the 11-layer convolutional deep neural network does very, very well with very few parameters and generalizes very nicely. And if you just have a 3-layer neural network, then it doesn't do so well, and it does worse than the fully connected network. Okay, so this is just a picture for you to believe me when I tell you that the choice of architecture is very, very crucial in observing the performance. And of course, in general, this type of studies are very useful because they tell you a little bit how the choice of a network influences its performance. But the reality is that wait. Let me get to the question. So why does it decrease even though you increase the number of parameters for the convolution? Yeah. So of course, I can only give you an intuitive explanation, right? So you're asking me about this, okay? You're asking me why does that? Sorry, where is the chat? Why does it decrease? Right? So you see there's a performance here decreases, right? But you see that also here the performance decreases. Yeah, so you can think of it this way, right? So on the 3 layers, in a sense, you have think about it in this concept. So in the 3 layers, you have, let's say, 3 steps to process the information. After 3 steps of processing information, you have to take a decision. Then the question is, let's say that you're trying to decide this data set, right? So here you want to count, for example, the number of horizontal lines. If you have 1 horizontal line, it's a 1. If you have 2 horizontal lines, it's a 4. If you have 1 horizontal line, it's 9. So you have to count on how many section of an arc you have, right? So here you have 2 sections of an arc. Here you have 2 sections of an arc, and so on and so on. So that's what the network should do is to start from the image and then extract some features which are useful for the classification. So it's clear that if you increase the number of parameters, but the number of steps is fixed, you are asking the network to learn many different representation of the information, but the process should still only last 3 steps. Okay. So then what happens is that if the network has too many parameters, then the network has too much freedom in finding these representations, and then the next steps they cannot settle on whether to pick the information from this neuron from that neuron. Okay, it's a very intuitive explanation. Okay, but you can understand that if in the true network you have 4 features that you want to calculate and take a decision on these 4 features, then these 4 features should be processed first, and then the next layers they elaborate over it. But now if you have 40 features, it is harder for the following layers to learn how to pick the correct representation to then process. Okay, so there is something that we're gonna describe in more details later, which is called overfitting. Okay, meaning that if you give a network too many parameters, the network is going to stop learning. Correct. So the network stops learning because it cannot find the correct path, right? It's like the paradigm of choice for humans, right? So if you go in a store and they have 10 t-shirts, you can choose the best t-shirt out of 10 t-shirts. But if you go to a store and they have a million t-shirts, how do you choose them? Okay. But this, again, these are sort of intuitive explanation from my perspective, right? From my experience. There is no correct mathematical answer to this. Okay. Good. So I was going to say this, that these type of studies are very useful because they tell you a little bit how the architectures compare. But the reality is that when the size of the network grows very, very large, then you cannot do this anymore, right? Because exploring architecture will just take too much time and will waste too much energy, and energy and resources. So nowadays, you're in a strange situation because you really have to gain an understanding of how to build a neural network from your own experience, how to choose the parameters, the activation function, the learning rate, the optimizer. We're going to see many of these many of these design choices later in the course, and it's a matter of experience. Okay, it's really a matter of experience, and that's why increasingly, right, we need a dedicated courses on deep learning, because the possible choice of architectures and features of the network are becoming so complicated that one has to always catch up with the literature and study it explicitly and see how people came to decide that a certain architecture is good for a certain problem. Okay. Okay, very good, guys. I think I'm done for today. I posted the slides on Slack. I'm going to send the video of the recording by Friday. Friday, you're going to get your first challenge. As I said, let me just repeat this. As I said, this is how I want to finish the class. Okay. Here, these are the leaders for challenge 0. Okay. So in challenge 0, I've asked you to please go and decide if you want to be the leader for this challenge. If you want to be the leader for this challenge, just take your name and you bring it to the leader position. Okay. So far, only group 1 has a leader. All the other groups, they don't have a leader. As I wrote in the message, being a leader for us, it means that you are focusing on communication and transmitting information across team members. Okay, for us, there is no particular idea that the leader is better than others, or that it's stronger than others, or that he understands more than others. It is nothing to do about that. And I think if you talk with some people that really work in organization, they will tell you that the role of the team leader or the role of your boss is not that one there of being better than you at your job. Is that one there of collecting information for people and then redistribute it across the organization. Okay, so please, I know that it's extra work to be a leader, and some people might not have this experience before, but it's really important for you to try to do this, to be in charge of, as I said, assigning the work to people, hear what they say, figuring out what are the problems, figuring out who needs help, what somebody says about a certain aspect of the challenge. It is very important because when you go to work, I think your role in the organization can only increase with your ability to communicate with others. Okay, so you can do an awesome job and sit at the desk for 10 years and then come up with a design for a blue LEDs that will change the future of the company. Okay, that's something that you could do, and this is a real story that you can look up. There was a story of the blue LEDs, the Japanese engineer, so on and so forth. Not important now, but if you're able to sit in a room for 10 years and come up with the design of the blue LEDs and communicate to all the rest of the organization through to the network of your coworkers, what are you doing and why what you're doing matters, and what are the obstacles that you can find, what are the resources that you need, you can only improve your utility toward the organization in which you want to contribute to. Okay, so please think about this, see which group you are, take your name, put it in first position. You're going to be the leader. Okay, the leader role is going to be to assign the job, to take contact with everybody, to make sure that everybody is working, to keep everybody on a certain deadline. Of course, it's more work. You have to keep emailing and checking your emails and checking your Slack, but it's a great experience. So please go ahead and do it. Okay. If you don't do it, then we just pick randomly, which is worse, because you could end up with a leader which doesn't want to be a leader, so he's not going to push himself to do a good job, and the outcome of the group is not going to be as good as it could have been if you decided to be the leader. Okay, good. That's it for today. Sorry that I talked too much. Hopefully from next time on, we can hear more about you and your presentation in class. I'm going to be here for 5 other minutes. If you have any questions, let me know. Otherwise, I'll see you guys next week. Okay? Say ciao when you leave, and otherwise, if you have any questions, let me know. Yeah, so let me give you the Slack. Give you the Slack for the course. Invite people. Invite people. Okay, link. Was there another question? Was there another hands up? Yeah. I'll stop the recording.